Morning, sir. Good morning, sir.
Good morning. One moment, I am sharing the link. I am sharing it. I am sharing the screen. Six completed, seven completed, 8, 9. From here. Yesterday we have completed the numericals up to here. This we have to start. In today's session, good morning students. Today's session, I am going to start moving charges and magnetism and magnetism. Moving charges and magnetism. Moving charges and magnetism. This is the yesterday up to this problem we have up to that before this one problem is there, up to there we have completed. Now I am going to complete the remaining numericals in it. The peak value is given. Peak value of EMF E naught is given as 220 volt. Peak value is 220 volt. Then no. Peak value is to be calculated. ERMS is given. Given one is ERMS. It is a 220 volt. To calculate the peak value, ERMS is equal to E naught divided by square root of 2. It is given E naught is equal to square root of 2 into ERMS. There we will take E naught is equal to square root of 2 will be equal to 1.414 into ERMS will be equal to 220. Therefore, E naught is equal to 311 volt. 311 volts it is. Right. Next. 440 ohms. It is given that resistance R is given as 40 ohms. Electric heater is connected to a power supply 220. Frequency F is given as 50 hertz. VRMS is equal to 200 volt. The peak value of electric current in the circuit is approximately. We have to calculate peak value of the current. Then IRMS is equal to this. I'll take it as instead of VRMS, ERMS I am writing. Both will be same. ERMS divided by resistance R. There. RMS value of current, IRMS is equal to ERMS is how much? 200 divided by R will be equal to 40. 40 that cancel in 200 how many times? 5 4s are 20. 5 times it will get cancelled. IRMS is equal to 5 amperes. IRMS is equal to 5 amperes. But they have asked what is the peak value of current. Therefore, we will take that. IRMS is equal to I naught divided by square root of 2. So I naught is equal to square root of 2 into IRMS. Then I naught is equal to square root of 2 1.414 into IRMS will be equal to 5. This is I naught is identically equal to 7.07. 7.07 we'll get it. 7.07 we will get. This is approximate value. Identically taken as 7. That's why this C option is correct. Next problem. The frequency of AC main supply in India, it is 50 hertz. In India, its frequency is 50 hertz. AC circuit instantaneous value of the EMF currents are given. Instantaneous values of the current. E is equal to E naught sin omega t. I is equal to I naught sin omega t plus phase angle phi. Then average power consumed. First of all, we have to take that IRMS and ERMS. Then E naught, I naught is given. I naught is given as a 1 and 1 ampere, and E naught is given as a 200 volt. So average power consumed. Average power is equal to IRMS into VRMS into cos phi. IRMS VRMS into cos phi. Power P is equal to IRMS will be equal to I naught divided by square root of 2. I naught divided by square root of 2. E naught divided by square root of 2 into cos phi. What is the phase angle? Phi is given as pi by 3. Then P is equal to, what is I naught? I naught is a 1. 1 by square root of 2 into E naught is equal to 200. 200 divided by square root of 2 into cos pi by 3 means cos 60. Therefore, P is equal to 200 divided by square root of 2 into square root of 2 will be equal to 2. Then cos 60 1 by 2. Cos 60 1 by 2. Therefore, we may cancel this. 2 that cancel into 100 times. 2 get cancel 100 50 times. Therefore, average power P is equal to 50 watt. 50 watt. Right. Next. An AC generator produces output voltage of E is equal to 170 sine 377 T volts, where T is in seconds. Frequency of the voltage is E is equal to 170 sine 377 T is there. On comparing this equation with standard equation, E is equal to E naught sine omega T. If you compare this omega is equal to 377, it's given. In the place of omega, what is given? 377. And we know omega, we may write 2 pi f. 2 pi f is equal to 377. Then f is equal to 377 divided by 2 pi. 377 divided by 2 pi. So this is f is equal to 377. 2 pi is equal to 6.284. This will get cancelled in it. This will get cancelled in nearly 60 times. 60 times. So 60 Hz is correct. A lamp consumes 50% of its peak power in an AC circuit. What is the phase difference between the applied voltage and the circuit current? Then power P is equal to peak power into cos phi. Power P is equal to peak power into cos phi. But it is given this power will be equal to 50% of the AC circuit. This power is equal to 50%, means what? Half of the peak power we will take. Half of the peak power is equal to peak into cos phi. So these two get cancelled. Then what is there? Cos phi is equal to 1 by 2. Phi is equal to cos inverse of 1 by 2. Then phi is equal to pi by 3. Means what? 60 degrees. B option is correct. Next, I will share these problems. So these are energy stored. The average power dissipated in the pure inductor of inductance L, when AC current is passing through it, is the average power dissipated. Average power dissipated in pure inductor of inductance L when AC is passing through it. This is average energy. Power is nothing but energy. Half Li square. This will be equal to half Li square. Average power is equal to half Li square we take. Next. This is completed. Okay. The next chapter is moving charges. And magnetism. Moving charges and magnetism. From this, first I'll come to that magnet. Magnet which attracts the substances like iron, nickel, cobalt is called a magnet, and the property of attraction is called as the magnetism. So north and south poles of the magnet. Suspended from a rigid support, it comes to rest by showing the geometrical north and south directions. The end of the magnet which shows the north is called as the north pole. End of the magnet which shows the geometrical south is called as the south pole. So this is about a bar magnet. Bar magnet has what's called, the magnet has some properties. One is that directive property. What is directive property? It shows that geometrical north and south directions. Second one is that attractive property. Similar kind of the poles, they'll repel one another, and the opposite poles attract one another. So attractive property. Third one is called as the inductive property. What is meant by inductive property? A magnet that induces the magnetic field in a magnetic material. A magnet that induces means what? It creates or it develops a magnetic field in the magnetic material. That will say inductive property. These are the properties of the magnet. So then whenever we take magnet, length of the magnet is taken as 2L. What is the length of the magnet? Separation between the two poles of the magnet is called as the length of the magnet. This is called as length of the magnet. So what is that? Geometrical length means actual length of the magnet. Physical length of the magnet is capital L. Capital L is called as the geometrical length. 2L is called as that length of the magnet. So geometrical length of the magnet is equal to 5/6 of the length of the magnet. Geometrical length of the magnet is 5/6 of the length of the magnet. Geometrical length is L. L is equal to 5/6 of the 2L. This is regarding the length of the magnet. When a bar magnet is bent in the form of a semicircular arc, a bar magnet is there. That bar magnet, if I bent in the form of a semicircular arc, let us suppose it is a bar magnet. A bar magnet that is bent into a semicircular arc. This is the north pole and this is the south pole. So then length of the magnet is distance between the two poles of the magnet. Length of the magnet is distance between the two poles of the magnet. This is R and this is R. So length of the magnet in this case is equal to Length of the magnet in this is equal to R. Then what is the geometrical length? Geometrical length of the magnet is this full. Geometrical length is the total length. How it will be there? This total length is called as the geometrical length. This total length is called as the geometrical length. This is called as direct distance between the North Pole and South Pole is called as the length of the magnet, right? So whenever we break the magnet into two parts, every magnet consists of the two poles, North Pole and the South Pole. The strength of the magnetic pole is considered as the magnetic pole strength, M. So magnetic pole strength unit is ampere meter. Okay. So whenever we break the magnet into two parts, each part will act like a magnet. Each part will act like a magnet. So this is the North Pole, South Pole, and this is South Pole, North Pole and South Pole. Like if I cut pieces and pieces and pieces, then also it will have North and the South Poles. Like monopoles, separate North, separate South Poles, they won't exist, right? So the length of the magnet we have discussed. What is the length of the magnet? Distance between the two poles of the magnets. Then whenever we take, this is the bar magnet, this bar magnet North Pole and South Pole, separation is taken as 2L. Magnetic pole strength of each pole is taken as a small m. Then magnetic moment is defined as the separation between the two poles of the magnet into any one of the pole strengths. This magnetic moment is a vector quantity. Direction of the magnetic moment is from the South Pole to North Pole. Magnetic moment is a vector quantity. It is 2L into M. Length of the magnet into any one of the pole strengths. Length of the magnet into any one of the pole strengths is called as magnetic pole. Any one of the pole strengths is called as the product of length of magnet any of the pole strength is called magnetic moment. Its unit is ampere meter square. Its unit is taken as ampere meter square. So when we cut this bar magnet, into two parts, let us suppose this is a bar magnet, consists of North Pole and South Pole. If I cut this magnet, if I cut like this, if I cut like this, so this, how many parts? 1, 2, 3. 3 parts we cut it. What about that new length of the magnet? Length of the each part will be length of the each part. After cutting, 2L dash is equal to 2L divided by 3. So length became 3 times. What about the pole strength? North Pole and South Pole are there. If we cut the magnet perpendicular to its length, then magnetic pole strength that remains same. Pole strength will be equal to same. Then what is the new magnetic moment of the each piece? 2L dash into M dash. That will be equal to 1 by 3 into 2L into M. That means the new magnetic moment of each piece, M dash is equal to 1 by 3 into 1 by 3 into M. So M dash is equal to M by 3. If a bar magnet is cut into 3 parts perpendicular to its length, then the new magnetic moment is M by 3. If you cut into 2 parts, M by 2. If you cut into 5 parts, M by 3. Like if I cut this bar magnet into N parts, if I cut the bar magnet into N identical parts, M dash is equal to M divided by N. If it cut into M identical parts, that M dash N identical parts, M dash is equal to M divided by N. Or if I take a bar magnet is there, And this bar magnet I am going to cut. It's a north pole and it is the south pole. North pole and south pole. Okay, north pole and south pole it is. So this is cut into 3 equal parts along its length. New length of the each part will be, what is that? New length of the each part will be how much? New length of the each part 2L dash is equal to, as it may cut into 3 parts, L divided by 2L divided by 3. No, length will be same. Length will be same for each and every part. So the magnetic pole strength M dash is equal to M by 3. It will be. Therefore, the magnetic moment M dash is equal to 2L dash into small m dash. Then M dash is equal to 2L dash means what? 2L into M dash is equal to M by 3. Therefore, M dash is equal to M by 3. Like this, we will take. Okay, most important. Now, if I take a bar magnet of magnetic moment capital M, this is important. Repeated problems are there. A bar magnet of magnetic moment M is there. This is cut into 3 equal parts. North pole and south pole I am taking. Let us suppose first one is that south pole and the second one is the north pole, like that I am taking. Then whose magnetic moment is taken as M. This is cut into 3 equal parts. This is cut into 3 equal parts. This is cut into 3 equal parts. Then each part magnetic moment will be M by 3, we will get it. Then these are arranged. These are arranged like a U shape. These are arranged like a U shape. South pole and north pole, south pole and north pole, south pole and north pole, like this. So this is the direction. This is the direction. See, vector notation, whenever we take, each part is how much? Whenever we cut into 3 equal parts, it will be M by 3. Its part magnetic moment is M by 3. Its magnetic moment is M by 3. Therefore, it is M by 3. It is M by 3. And this is also M by 3. Like this. M by 3, M by 3, like that we are taking. Now, if you take the vector notation, I'm taking vector notation. This is a vector downwards, means along the negative axis. This is along the positive axis. This is along the negative positive axis. See how we'll take that coordinate system. If I take the coordinate system, this is a positive x-axis. This is a negative y-axis. This is positive y-axis. Then positive y-axis means positive. This is taken as M by 3. This is M by 3. These are, one is along the positive y-axis. This is along the positive y-axis. This is along the negative y-axis. Equal and opposite. If the two vectors are equal and opposite, they'll cancel one another. Then this part magnetic moment is M by 3. Therefore, the resultant magnetic moment of system is taken as resultant magnetic moment M dash is equal to M by 3. M dash is equal to M by 3. Like a bar magnet of magnetic moment capital M is cut into 5 equal parts. It is a bar magnet, consists of the south pole and the north pole. It is cut into 5 equal parts. And these parts are arranged like a shape S. They have arranged like a shape S. Like this, they have arranged. Each path magnetic moment will be m by 5. This is important, asked many times. M by 5. Each path magnetic moment is m by 5. M by 5. M by 5 and m by 5 like this. Each path magnetic moment. See, equal and opposite. We cancel these two. This vector and this vector, they are parallel to one another. Means we'll add them. M by 5 plus m by 5, it will be 2m divided by 5. So the resultant while we are taking, two vectors are like this, two vectors are like this, and one vector is like this. The resultant is right angle to one another. This is 2m divided by 5, and this is m divided by 5. So resultant vector m dash is equal to square root of 2m by 5 whole square plus m by 5 whole square. Then m dash is equal to square root of 2 2s are 4, 4m square divided by 5 plus m square 5 not, it's 25. M square divided by 25. These are direct problems. No need to solve the problems extra. These are direct problems. Square root of 25 m square 4 plus 1 5. 25 not 5 m square. Taking 25 LCM, it will be 5 m square. 5 that cancel 25 5 times. Therefore, m dash is equal to square root of m square divided by 5. That will be m by square root of 5. Like this, they will ask, right? If the bar magnet is cut into two parts and two parts are inclined at an angle theta, then also we can calculate. Let us suppose a bar magnet of magnetic moment. It is a bar magnet. This bar magnet consists of the south pole and north pole. These are inclined. These are cut like this and inclined. These are placed like this. This is S, N, S and N. Angle between them is 90 degrees. Then as it is cut into two parts, it is m by 2 and it is m by 2. So angle is 90 degrees. Therefore, the new magnetic moment m dash is equal to m by 2 whole square plus m by 2 whole square. Today's class is up to 8:30. M dash is equal to square root of all these days up to Saturday. I'm going to take up to 8:30 and I'm going to complete this syllabus by Saturday. M square divided by 4. So therefore, m dash is equal to square root of 5m square divided by 4 we will get. So m dash is equal to 5 by 5 by no. M 2m square. M dash is equal to square root of 2m square divided by 4. That is, this will get cancelled. M dash is equal to m divided by 2. The new resultant magnetic moment is m divided by 2. It is like this. Okay. When a bar magnet of magnetic moment capital M is cut into, I will share you that detailed synopsis. Today few synopsis, tomorrow few synopsis I'll make and I'll share you. Then this is the north pole. Let us suppose a bar magnet. It is a bar magnet of magnetic moment capital M is to take that south pole and north pole. If this bar magnet is bent into a semicircular arc of this bar magnet is bent into a semicircular arc. This is the south pole and this is the north pole. It is made like this, south pole and north pole. Then the new magnetic moment, its magnetic moment is taken as m. M dash is equal to 2m sine theta by 2 divided by theta. This is the new magnetic moment of the system. Once again, I'll repeat. A bar magnet of magnetic moment is there. It is a bar magnet. Bar magnet, south pole and north pole are there. South pole and the north pole are there. And if I bend this bar magnet into an arc of length, it is bent into an arc of length. If it is bent into an arc of length or an arc which makes a radius r at the center, this is theta. Then south pole and the north pole. This is south pole and the north pole. Then the new magnetic moment of this one is 2m sine theta by 2 divided by theta. This is okay. So when we take that bar magnets, they are placed end to end. Then the resultant magnetic moment, we'll see that. Let us suppose this is a bar magnet, one bar magnet. It is the another bar magnet. These are kept in contact. With the like poles we may keep in contact, or unlike poles we may keep in contact. This is that south pole and the north pole. South pole and the north pole. So these are south pole, north pole, south pole, north pole. This is M1 and M2. They are in the same direction. Then the new magnetic moment M is equal to M1 plus M2 we may take. If I take the two bar magnets, this is a one bar magnet. This is that another bar magnet. This is the other bar magnet. South pole, north pole, south pole, north pole and south pole is to take that. North pole and south pole. The magnetic moment of this one is taken as M1. And the magnetic moment of this one is taken as M2. Like this. The new magnetic moment M dash is equal to M1 difference M2. M1 difference M2 means if F1 M1 is more than M2, M1 minus M2. If M2 is more greater than M1, that will M2 minus M1 will write. Next. We'll take that a bar magnet. This is a bar magnet, and this is another bar magnet. Another bar magnet. This is taken as south pole and north pole. South pole and north pole. Same. Then M1 and M2. The resultant is M dash is equal to M1 plus M2. M1 plus M2. Like this we will take resultant. Right. Next. When the magnets are connected like this, equal magnetic moments, they are connected like this, the resultant magnetic moment will be 0. If we take that, this is a bar magnet. If these are connected like this, it's a magnetic moment M, and M like this. This is M, this is M, and this is M like this. The new magnetic moment is M dash is equal to 0. This is M dash is equal to 0. The new magnetic moment M dash will be equal to 0. This is the, so like if I take the magnets with the different magnetic moments. See, I am going to take, this is a bar magnet of magnetic moment M, and this is taken as 2M. This is taken as 2M, and this is taken as 3M. If the bar magnets, they consist of M, 2M, and 3M. M, 2M, and 3M. Then this we may write how to redraw this one. This is a bar magnet. This is that bar magnet. This is a like 3 magnets. It's a magnetic moments M, M, M. So what about that net magnetic moment due to this? It will be 0, right? Then plus this side one magnet extra is there. This side one magnet extra is there. This is the one magnet, and this is one magnet. This is how much it is. This is M, and this is 2M. How they are? They are inclined at an angle theta. Inside angle is 60 degrees, but these are not co-initial or not coterminous. For co-initial vectors and coterminous vectors, inside angle will take that. If they are not co-initial or coterminous, exterior angle is to be taken. 120 degrees we have to take that. Therefore, the resultant magnetic moment. For this, the resultant magnetic moment M dash is equal to 0 plus. These are how they are. These are inclined at angle of 120 degrees. This will be M square means what? 2M whole square plus M square, A square plus B square, P square plus V square, like plus 2 into 2M into M into cos 120. Then M dash is equal to square root of 4M square plus M square plus 2 2s are 4, 4M square cos 120, cos 120 minus 1 by 2. Cos 120 minus 1 by 2. Therefore, M dash is equal to 2 that cancel and 4 2 times. Therefore, M dash is equal to 4M square plus M square. It will be 5M square. 5M square minus M square. 5M square minus M square. 2M square, sorry, 2M square. So M dash is equal to square root of 3M square. Nothing but square root of 3M. Square root of 3 into M, that we will take. Next. We take this magnets like this. Magnetic momentum is completed. Magnetic induction. Magnetic induction or magnetic flux density. Force per unit magnetic pole strength is called as the magnetic induction. Its unit is Tesla or Weber per meter square. Weber per meter square. Like this, we may take. So, right. Whenever we take that magnetic, whenever we take this, the magnetic flux phi, magnetic flux phi. Phi is equal to B bar dot A bar. Phi is equal to B bar dot A bar. Phi is equal to BA cos theta. Based on the theta, flux may be positive, maybe negative, maybe 0. That we will take, right? So when a bar magnet is taken, the magnetic moment along the axial line. What is axial line and what is equatorial line? Let us suppose it's a bar magnet. Is considered as the South Pole and North Pole. It's a South Pole and a North Pole. A straight line which passes through it is called as the axial line. This line is called as the axial line. A straight line which is perpendicular to it is called as the equatorial line. This is called as the equatorial line. This is called axial line and this is called as the equatorial line. Then magnetic induction at a point on the axial line. BA is equal to mu naught divided by 4 pi, mu naught divided by 4 pi into 2md divided by d square minus L square. D square minus L square whole square. Magnetic induction at a point on the equatorial line, B equatorial is equal to mu naught by 4 pi into m divided by d square plus L square whole power 3 pi. D square plus L square whole power 3 pi. This is the magnetic induction. Next, so when we take the relation between magnetic, when we take that intensity of magnetization is magnetic moment per unit volume. Its a unit is taken as ampere meter square. Magnetizing field or magnetizing force, H. Magnetizing field or magnetizing force, H is equal to B divided by mu. This unit of this one is also ampere per meter, sorry. Ampere meter square, not ampere per meter. This unit is ampere per meter and ampere per meter. Its unit is also taken as ampere per meter. Like this we will take. So mu is called as the permeability of the free space. Mu r is called as the relative permittivity. Mu r is called as the relative permittivity. The relative permittivity is nothing but ratio of the permittivity of a medium to the permittivity of the free space is called as the relative permittivity. See, I have to take that. This I is the intensity of magnetization. H is the magnetizing field or magnetizing force. Then magnetic susceptibility chi is I by H. Magnetic susceptibility chi is equal to I by H. It has no unit. So what is this? It is a ratio of intensity of magnetization to intensity of magnetizing field. It is based on the susceptibility. The magnets are classified as para, ferro, and dia. What are called diamagnetic substances? They are repelled by the magnets. What are called paramagnetic substances? They are attracted by the magnets. What are called ferromagnetic substances? They are strongly attracted by the magnets. They are strongly attracted by the magnets. One moment. This every time it's disturbance to you. So based on the susceptibility, magnets they have classified para, ferro, and diamagnetic substances. So okay, so whenever current flows through a conductor, magnetic field will be developed around the straight conductor. Let us suppose flow of current is like this. In a conductor, current is flowing like this. Around it, magnetic field will be developed. Is it? So the direction of the magnetic field is like this. If it is the current carrying conductor, this is the current carrying conductor and the magnetic field. If you take that magnetic field, it will be like this. Magnetic field is like this. If you hold the current carrying conductor, magnetic field will be like this. Right. This is the direction of the magnetic field. It is given by Ampere's right hand rule. If you hold a current carrying conductor in your right hand, then thumb represents the direction of the flow of current, and the curled fingers they represents the direction of the magnetic field. Let us suppose a straight conductor is there. It is a straight conductor. In the straight conductor, current is flowing. We have to hold this straight conductor like this. Then we take that magnetic field here at the point P and at the point Q. So inward magnetic field is represented like this, in. Outward magnetic field is represented like this, out, like this. Okay. So if you hold like this, the curled fingers they represent the direction will be like this. Curled fingers direction will be like this. So at the point P, outward magnetic field will be there. At the point P, magnetic field is outwards. So we'll take that it's an outward magnetic field. At the point Q, magnetic field is into that. It will show that magnetic field is into. So this inward magnetic field will be there at Q and outward magnetic field is there at P. So the direction will be like this. The direction of the magnetic field will be like this. So at the P, outwards. At the Q, inwards. The magnetic field will be there. Right? If the current is flowing in a circular coil, this is the circular coil. If the current flows in it in the clockwise direction, if the current flows in it in the clockwise direction, this magnetic field is inward magnetic field will take that. If the current flows outwards, inward magnetic field is taken like this. Inward magnetic field is taken like this. This is like whenever we take, if the current is flowing in it in the anti-clockwise direction, if the current flowing in the anti-clockwise direction, so then magnetic field is outwards. Outward magnetic field is there. If the current is flowing in anti-clockwise direction, magnetic field is outwards. If the current is flowing in the clockwise direction, magnetic field is inwards. Inward means into the plane of the board that will take. According to Biot-Savart's law, next important one it is Biot-Savart's law. Biot-Savart's law. According to Biot-Savart's law, in the magnetic induction due to a current carrying conductor, let us suppose it is a current carrying conductor. The current flows through it is taken as I. I is the flow of current. This is a small portion of the conductor I have taken. From this conductor, at a point, at a distance R, a point P is taken. At a distance R, a point P is taken. It makes an angle theta. Therefore, the magnetic induction at the point P, dB is equal to mu naught divided by 4 pi into ideal sine theta divided by R square. Ideal sine theta divided by R square will take. This is the Biot-Savart's law. This is the Biot-Savart's law, right? So this dB bar, if you write in terms of the charge, velocity, and magnetic induction, this we may write in other terms. dB bar is equal to mu naught divided by 4 pi into Q into V bar cross B bar divided by V bar cross B bar divided by R cube. V bar cross B bar divided by R cube. Okay. So when we plot the graph between the magnetic induction distance, the graphs will be like this. Let us suppose if I plot the graph between the magnetic induction and current, magnetic induction and the distance. If I plot the graph between the magnetic induction and current, the graph will be like this. And the current, the graph will be like this. If I plot the graph between the magnetic induction and distance. If I plot the graph between the magnetic induction and the distance, magnetic induction is taken along the y-axis and distance is taken like this. Therefore, the graph will be like this. The shape of the graph will be like this. Or if I plot the graph between the magnetic induction and 1 by B and the distance 1 by R square. Magnetic induction B and distance 1 divided by R square. Therefore, it is a straight line. It's like this. Straight line you have to take. It's a straight line. These are the graphs. Fine. When a straight conductor carrying current, this is important. Based on this, many problems are there. Let us suppose a straight conductor is carrying current. Flow of current in the straight conductor is taken as I. I is the flow of current in the straight conductor. I is the flow of current in the straight conductor. Then the magnetic induction. Then the magnetic induction at the point P. Magnetic induction at the point P. I is the flow of current. Then theta 1, theta 2 we are taking like this. Theta 1 and theta 2. They are like this. And these are taken as alpha and beta. These are taken as alpha and beta. Okay, magnetic induction at the point B, at the point P we require. Magnetic induction at the point P is equal to mu naught I divided by 4 pi R. Mu naught I by 4 pi R into sin alpha plus sin beta. Sin alpha plus sin beta. It is a finite length conductor. If length of the conductor is infinite, if the length of the conductor is infinite, length of the conductor is infinite, and then alpha is equal to 90 degrees and beta is also equal to 90 degrees. From the above formula, how to write this? Alpha is 90 degrees, beta is also 90 degrees. So B is equal to mu naught I divided by 4 pi R into sin 90 plus sin 90. Sin 90 becomes 1. Therefore, B is equal to mu naught I divided by 4 pi R into sin 91 and sin 91. Therefore, B is equal to this 1 plus 1, 2. So, mu naught I divided by 2 pi R. Mu naught I divided by 2 pi R we will take. It is. So, if the point is there on the axis, let us suppose it is a conductor. On the conductor, if the point P is there, if the point P is there on the conductor, then the magnetic induction dB will be 0, or magnetic induction B is equal to 0. At this point, at the point P, if it is there on the axis, then magnetic induction will be 0. Magnetic induction will be taken as 0, right? For the, this is also important. For the, this is when the point is on the axis. If the point is on if the point P is at one end, of infinite long straight conductor. Then B is equal to mu naught I divided by 4 pi r. B is equal to mu naught I divided by 4 pi r. B is equal to mu naught I divided by 4 pi r. That will take. So then, according to Ampere's circuit law, the magnetic induction B bar dot dl bar, according to Ampere's circuit law, the line integral of the magnetic field around any closed path, is equal to mu naught times the net current enclosed by the surface. This is called Ampere's circuit law. This is called as Ampere's circuit law. Okay. So whenever we take that, current is flowing in a rectangular square. Current, if it is flowing in the square of side length taken as A, every side length is taken as A. A is the side length. Then magnetic induction at the center, it is anti-clockwise. If it is anti-clockwise, outward it will be there. Then side length A is there. The magnetic induction at the center is B is equal to 8 root 2 mu naught divided by 4 pi into I divided by A. These are direct formulas. Magnetic induction at the center is 8 root 2 mu naught by 4 pi into I by A. If you want to prove, we have to take for every line and we can calculate it. So mu naught 8 root 2 into mu naught by 4 pi into I by A. So instead of that, if it is like a triangular shape, a triangle if I take, this is the flow. Side length is taken as A, current is flowing like this. Every side length is taken as A. Then the magnetic induction at that center, due to this will be B is equal to 18 mu naught by 4 pi into mu naught divided by 4 pi into I by A. B is equal to mu naught by 4 pi into I divided by A. This is okay. So when the two straight conductors, they are carrying currents. If the two straight conductors, they are carrying currents. These are the two straight conductors, they are carrying currents. They'll repel one another. Why? The flow of current will be like this. I1 and I2 are the currents flowing through them. So at a particular point, if I take, what about that magnetic field? The magnetic field at this point is like this. Currents there. These are opposite directions, means attraction. They'll attract. So the magnetic field at this point, due to this, when the current is flowing in the conductor A and B, So if the current flows in a magnetic field is like this. If the current flows in it, the magnetic field will be like this. This is the magnetic fields at this point. So that's why they will attract one another. If the parallel straight conductors carrying currents, they will attract one another. Then the resultant magnetic force between them or magnetic induction at them, if you want to calculate. First, we'll calculate the magnetic induction at this point inside. At this point, we'll take that at the point P, magnetic induction. B is equal to mu naught divided by 2 pi into mu naught by 2 pi into the point P. We are taking at a distance of x. Separation between the two conductors is taken as r. This is taken as x. Then what about that distance? What about this distance that will take? This distance is equal to r minus x. This distance is equal to r minus x. Then I1 divided by x plus difference I2 divided by r minus x. This is the magnetic induction at this point. When the straight conductors, they are carrying currents in the same direction. So these are attraction, because magnetic field due to this at this point inwards, magnetic field due to this it is outwards. So inward and outwards are there, opposite were pair. That's why the opposite poles they attract one another. Next, if the currents they are flowing in the conductors in the downwards, one is upwards, one is downward. If the currents are flowing in it are taken as these are the two parallel straight conductors, flow of current will be there in it is along the upwards, and flow of current in it is taken as I2. These are. So at the point P, I want what is the magnetic induction. One moment. I'm going to mute. Sorry. Okay. See, after most important part is there. That is most important. Bar means when the current is flowing like this. When the current is flowing in the conductor, what is the magnetic induction like that? They will ask. These are the direct problems that we will take. The direct problems. These are. One moment. Right. Okay. Whenever we take, this is the distance x, this is the r minus x, x and the r minus x. Let us suppose separation between them is taken as r. This is r minus x. This is r minus x. Therefore, we'll take that magnetic induction at the point P is magnetic induction at the point P is mu naught divided by 2 pi into I1 divided by x plus I2 divided by r minus x. This is a magnetic induction. Okay, here important based on these products they are asking. Please note down that this point what I say, please note down it. Write down a wire which is bent in the form of, please note down, a wire which is bent in the form of an arc, a wire which is bent in the form of an arc, who subtending an angle theta at the center, then the magnetic induction at the center is, a wire is there, wire we have bent in the form of a circular arc which subtends an angle theta at its center. Then radius is taken as r. For the circular arc, radius is taken as r. Then the magnetic induction at this point. So B is equal to mu naught Ni theta divided by 4 pi r. This formula please note down. B is equal to mu naught Ni theta divided by 4 pi r. For n turns, this is for n turns. For a single turn, n is equal to 1. Therefore, the magnetic induction B is equal to mu naught I theta divided by 4 pi r. Mu naught I theta divided by 4 pi r. So based on the theta, it may be there. For example, if you take that it is a semicircle, if it is taken as a semicircle, for a semicircle, if you bend in the form of a semicircle, current is flowing like this. Then the magnetic induction B is equal to mu naught I into semicircle means pi. Semicircle will be equal to pi radians or 180 degrees. So mu naught I pi into 4 pi r. Both in numerator and denominator we will cancel pi. Then what is there? That will be equal to mu naught I divided by 4r. The magnetic induction at the center. The magnetic induction at the center. At this point, the P. Mu naught I divided by 4r. If it is a quadrant, it is a quadrant means 90 degrees. The angle is taken as pi by 2. If the wire is bent in like a quadrant, at this point, what is the magnetic conduction? They'll ask it. So for this, in the place of theta, we have tried pi by 2. Therefore, B is equal to mu naught I into theta will be what? Pi divided by 2 into 4 pi r. Therefore, B is equal to mu naught I. Pi and pi get cancelled. Pi and pi get cancelled. Mu naught I divided by 8r. Like this. Right? This is important. Next. Next, we will take that. Let us suppose this is the semicircular one. If the current is flowing like this, this is the semicircular one. This is taken as a semicircular one. So magnetic induction at this point we require. Magnetic induction at this point we require. So for that, we take different points. B1. So when current flows through it or through this, that will take B1, B2, and B3. B1, B2, and B3. So therefore, we write B1 is equal to 0 and B2 is also equal to 0 because this is because they are on the axis. I told you whenever this is that current carrying conductor, if the point P is there on the conductor, what about the magnetic induction? dB is equal to 0. Okay, so then we'll take dB1 is equal to 0 and dB2 is also equal to 0. Next, the magnetic induction due to semicircular one, we have to take that B2. We'll take that B1 is equal to 0 and B2 is also equal to 0. dB not required. Okay. B2 will be equal to B2. It is semicircular path. So semicircular path means what? If you take that semicircular path, B2 is equal to mu naught I into semicircular path means pi divided by 4 pi r. So both the numerator and denominator pi gets cancelled. B2 is equal to mu naught I divided by 4r. Mu naught I divided by 4r we will take. This is that magnetic induction. Instead of that, if it is the loop like this, this is the loop. We'll take like this. This is a loop and this is then current is flowing like this and it is in anti-clockwise direction. It is in anti-clockwise direction. Then the magnetic induction at the point O is B is equal to mu naught divided by 2r into 1 plus 1 divided by pi. How does it will come? So it is the combination. For this point, for this it is B1 and it is taken as B2. So it is a straight conductor. carrying current. Current. Then magnetic induction at the point P, at the point O will take it. It is the second one is that circular one. It is a complete circle. For the complete circle, magnetic induction at the center, we have to take it. Right? So combined, we have to take that combined one. Magnetic induction B1 is equal to mu naught I theta, mu naught I. It is at one end. If it is at one end, mu naught I divided by 4 pi r. Mu naught I divided by 4 pi r. This B2 is equal to mu naught I divided by B2 is equal to mu naught I divided by 4 pi r. 4 pi r. B1, B2. So B3, this is taken as B3. B3 is equal to mu naught I divided by. So 2 pi radians, that mu naught I divided by 2r. So then we have to take this. B1, B2 will be equal to B1 plus B2 is equal to mu naught I by 4 pi r, mu naught I by 4 pi r, mu naught I divided by 2 pi r. This is what is the resultant magnetic induction. B is equal to B1 plus B2, then plus B3. R taking this mu naught by 2r plus mu naught by 2 pi r, we will get like this. Okay. Right. If I take that a semicircular one like this, if the current is flowing like this, current is flowing and it is like this. So magnetic induction at the center will be zero. Will be zero because this is B1 is equal to 0 because this point is on the axis. B2 is also 0 because this point is on the axis. So here it will be the magnetic induction B3. B3 is equal to mu naught I divided by 4r, and B4 is equal to mu naught I divided by 4r. How these are? This current is flowing in it is clockwise, and then it is current is flowing in the anti-clockwise direction. This is a clockwise. This is what? Anti-clockwise. So one is clockwise and anti-clockwise. Magnetic induction B is equal to B1 plus B2 plus B3 plus B4. B1 plus B2 plus B3 plus B4. So B is equal to 0 plus 0 plus mu naught I divided by 4r. This is one is clockwise, one is anti-clockwise. So there we take that minus mu naught I divided by 4r. This mu naught I by 4r get cancelled. Then magnetic induction at the center will be 0. Right? If I take a circular portion is like this. At this point, current is, let us suppose it is flowing in the anti-clockwise direction. So this is like this. Magnetic field due to this one is 0 because it is on the point. So due to this one also will be 0. Due to this 0 and due to this also will be 0. Right? Then this we are taking, radius is taken as R2. This radius is taken as R1. R1. Therefore, magnetic induction B is equal to mu naught I divided by semicircular 4, mu naught I divided by 4 into 1 by R1 minus 1 by R2. like this will be there. Okay, I'm going to stop the class here. We'll see that remaining part in the next class. Thank you.